Let's explore some more in R with sampling. And this time we'll do sampling of populations different than the jars of 0, 1, or -1, 0, and 1. So maybe to start, let's create some samples from a normal distribution. Bunch of samples with a mean of 50 and a standard deviation of 2. So this function should look similar and familiar to what you've seen before. One normal distribution, number of samples, the mean, and then the standard deviation for those samples. So we can see we got a vector created of samples. Now we can do different operations on that. This is kind of similar to how we did things before. Mean of the samples. Not surprisingly, it's right around 50 because we sampled so many times. We can do a standard deviation of samples. Again, not surprising, it's very close to 2. We can also do a histogram. And that's a nice, well-balanced histogram of right around 50. So let's look at another distribution. Here's some test data that I created, for example. So if we look at a histogram of test data, you can see it's kind of distributed but tilted, if you will. It's kind of like there's more to the left than the right if we kind of take a look at the average of test data. So the average is 21, so it'll be right around here. So you can kind of see that based on the average, it's not kind of this normal distribution. It's kind of maybe is tilted or skewed from one side to the other. So there's this package called moments that lets us understand this tilting a little bit. So I'm loading it. I got the warning message because I've loaded it multiple times. Now I'll use the moments package. So that's what we needed. So now we have this. We have the moments package. So now with the moments package, we can do something called skewness of time, or test data, sorry, which is a variable up there. What do you think skewness will return? It's kind of showing how it's skewed or tilted, if you will. Tilted is maybe not the right word. Shifted is probably a better word than tilted on the distributions. So the normal distribution is kind of evenly distributed on both sides of the mean typically. Now this test data distribution is not evenly distributed on both sides of the mean. Right, so you can have more samples on one side or the other compared to the mean. So that's just something to be aware of when we're looking at distributions. So they're not always kind of the Pareto distribution of the states. They're not always normal distributions. They could be skewed to one side or the other. Speaking of states, let's use our read states function. So this should look familiar to you. We kind of wrote this last time. So I'm using my function called read states that reads in the CSV file from the government census area and then cleans it up by removing the rows and columns that aren't useful, making sure they're numbers, as you can kind of see up here as well, and then returns that. So we can kind of run that. And we could say, for example, oops, wrong keys. How about df read states using my function. And now we have df states. 21 observations of 5 variables. Just in case you've forgotten this data set, here are the different census numbers and the different numbers for all the different states and the states' names. So now we can do a bunch of different things on this. We can do, as we could before. So we have df states, df states dollar. Let's use that one. So that's the mean, for example. But we can also do sampling. So we could, let's just sample df states. So we're going to sample from that vector. And we'll do 16 is just a number, and replace equals true. So those are the numbers that we're doing the sampling from. And just like before, we can generate a mean of those. So remember, this is the real mean, and this is our sample mean when we're doing 16. If we did it again, get different numbers. And if we increase the sample size, the number of times we're sampling, it might get a little closer, as we can see. See, that number is closer, but it depends each time as we do it. Another way to let's have some fun with this. How about if we sampled 51, we had this equals false. So if we did this command, what will the mean return? As you can see, the mean of this is exactly the true mean, and that's because we sampled 51 values and we placed equals false. So each time we picked one out, by the end of 51, we've sampled all of the numbers. So that's kind of another way to think about how we're sampling here. Typically we're doing replace equals true, so we can kind of keep drawing the same state, if you will, multiple times. And we can kind of do the same types of operations on the states that we were doing for all the other distributions. So rather than generate a mean, we can store the values here. We can say sample vector, for example, and let's do histogram of v. See, this kind of looks like the Pareto distribution, right? This looks like the state distribution. And just to remind you what the states distribution looks like, we can pull that out as well. Looks kind of the same. Now let's make it where replace equals true. It's still similar because we have the size of 51. We can do it again. It's not substantially different. Now if we have the size of 16, which we started out before, each time we do it, it's going to be a little bit different. And then let's take a look at the results. Sorry, there we go. See, big difference. So sometimes it's going to be accurate or not because the sample size is much smaller. That's kind of how we do that. And then we can do the same thing with our replacing, or replicate, to be more precise. So we can have, oops, I have to spell it right, replicate. How many times should we do this? How about 100 times? And what do we want to do here? How about the mean of the samples? We'll have simplify equals true. The mean of v, you would expect that to be fairly close. And let's, what does this look like? So if we take a look at the histogram of the vector v, which is the 100 means, what do we expect that to look like? Do it again just to see the difference. And in fact, we'll make it 1,000. Look at that. It's a normal distribution because we're taking the mean of the means, not the mean of the actual distribution. Doesn't really matter. Make this a little less. It's not going to be as accurate. So we can kind of get a feeling there again. So the mean of the means is going to be normally distributed, but the mean of the actual, the distribution, sorry, of the mean of the means is going to be normally distributed because the actual sampling process is going to be a normal function. So we've kind of just done again basically different ways to sample and replicate those sampling and looking at the results. So we kind of typically take mean of means and look at the distributions and means of that. And by doing this, we can get a feeling for how kind of populations look like and how they behave, and get a feeling for kind of the sample out of the entire population and what that entire population looks like.